Okay, this is the digital image processing lecture number 12. In this lecture, we are talking about image transformation, which is Fourier transform. First, we are talking about Fourier transform, and then for other transformation in digital images. Now, starting from Fourier transform in image, first we are talking about the we're talking about the one-dimensional Fourier transform. One-dimensional Fourier transform is defined like this formula, and maybe this one, and this is f, large F, and small f. Is about integration, and then this is the inverse transformation. J is root minus 1, and this is amplitude of the image, which is r squared, real part square, imaginary part square, and root mean. And for the phase is arctangent imaginary to real one. This is the phase of the image, which is important, of course, later I will show you. Okay, then next is the, for example, is a constant signal like this rectangular signal with the amplitude A, which is this. So Fourier transform after manipulations is this becomes sync of this over the same sync alpha or alpha. It is sine alpha or alpha, which is sync function. So it is the kind of this main with main lobe and several side lobes. This is the Fourier transform of this rectangle. This rectangle, the Fourier transform is here. Okay. Then, if we go to discrete Fourier transform, in discrete Fourier transform, we have the waveform is like this. We sample first by Nyquist rate or more than Nyquist rate, and then we have discrete, and instead of integration, we use summation here. For instance, we have finite number, which is 0 to n minus 1, that is n samples, and then this Fourier transform discrete and inverse of that. For two-dimensional discrete Fourier transform, also we have double summation, like this x and y become u and v. And the inverse is this. And this is discrete Fourier transform of image to dimensional. And this is an example. For instance, we have Nina image, original image, and its magnitude Fourier transform, and its phase image, phase transform, which later I will show you that the image has several, more information than more important information actually. Later I will show this. This is 512 by 512 linear image. For instance, in this case of Saturn image, because its dynamic range of the magnitude is too high, so we use this logarithmic transformation and then a factor of c, then we transform this one into this one. This is not transformation, this is just scaling with this transformation, log transform, in order to show the detail like a diamond. This is the Fourier transform on Saturn, like this, with after this transformation. And there are many properties of the Fourier transform, as in one dimension, we have in two-dimensional also. First, it is separatable. We can use for u and v separately the Fourier transform. First, for x and v, and then x and v, and then for uh, u and v, like this. So it is first horizontal, we take for horizontal transform, and then we took vertical transform. So it is separatable transform. It is one of the kind of separatable transform indication. And uh, another property is rotation. Rotation is very important because if you have the original image like this, the in the polar coordinate r cosine theta, r theta, we have r theta. If rotate by theta 0, for instance, 45 degree here, then the frequency domain also rotate by the same amount of 45 degrees. And then convolution, as in one dimension, convolution integral. I talked about convolution integral in previous video, that it is defined like this, and then this convolution is useful for reducing the number of number of calculation. For instance, if the convolution is very complicated uh, manipulation in mathematical, and then you can, if you transform to the Fourier transform frequency domain, then it is multiplication, and again vice versa. Convolution in Fourier transform become multiplication in time domain, which is kind of windowing in window, and this kind of thing we can use this. Other separatable, but here I want to stop here and then show more about the other thing of the book. Here is this example. Then you can study this, and this is two-dimensional example. And this is another example here. Also, there are several examples. This is in the spatial domain, space domain. I mean, the spatial domain means a space domain. And this is Fourier transform. A single line become like this. A double dot become like this, and like this. This is in image form, and this is in its Fourier transform form, where we show here only magnitude. And then sampling comes in one-dimensional. As you know, the Nyquist rate is the minimum rate, is the double of the maximum frequency, is the Nyquist frequency. As in single, well, if you have this curve like this, you sample this with these samples, and then if you have enough sampling, then you can recover. This is another example of Saturn I show you, and after this scaling become more visible like this. This become like this. And then another property is translation. If you translate in U0, V0, then you move the frequency by minus U0 and minus V0. Vice versa in the time domain, if you make minus X0, Y0, then the phase will be changed by this amount. The separability, and also the periodicity is so important, because if you have the finite sequence of the number in one dimension, for instance, a finite with n and repetition n sample, then with that periodicity with repeat. So if you show in the frequency domain, this is base band, and then this is the multiple of that uh, number of n. You repeat the spectrum up to infinite. Also, rotation is this one. I show you rotation. If you're in polar coordinate like this, then in the frequency domain, rotate that by the same amount of rotation. The example is here, here, rotates, and then frequency domain also rotates. We can study the book because we don't have much time. And then the sampling, I told you you have to put enough number of samples as in one dimension, also in two-dimensional convolution and two-dimensional convolution here. Also sampling, if you have enough sample, if you don't have enough sampling, then you will have the problem of aliasing. So the aliasing you cannot recover from the frequency domain back to the time domain, or if you don't have the enough number of sample. If you have more than enough, then the spectrum are far and not overlap. Well, at least should be 93, which is twice the number and twice the maximum frequency or maximum uh, variation in the image, variation in image spectrum, like this. This is in one dimension. In two dimension, for instance, you can suppose that we have a needle like this. We are sampling the pixels of the image. If you have enough pixels, you can recover because the spectrum doesn't overlap like this. It's separated. At least they should be touched together. Then it's enough sampling for two dimension. This you can study. Also, for implementation, because we are using implementation, if the Fourier transform use a lot of computation. So in this case, if you or the number of computation is n square or more than n square, then by fast Fourier transform, it become n log n base 2. So you can reduce, maybe if you increase the number, even it's more than 100 times smaller number of multiplication, which is good for implementation in real time, especially uh, number operation, and then inverse Fourier transform, and so on. That you can study about this. And so this is other point of the separatable image that it will be the topic uh, for the next uh, next top. Yes, other separator like Walsh or Hammer transform or slant transform, and especially the eigenvalue transform is very important for compression of image and also for detecting the shape of the image, detecting the contents of the image, that what contents is. But we do not go here, just stop here. In this, I stop here and thank you very much.